Good afternoon, everyone, and welcome to today's webinar on pressure management, save your assets, save your energy, building a rapid return on investment. Today's webinar is being recorded and will be shared with all of you tomorrow. If you have any questions, please go ahead and type them in the questions box below, and we will take questions at the end. Your presenter for today is Dave Kanter with Trimble Water. He is our West Coast Regional Business Manager. Okay, Dave, over to you.
Great, thanks, Lindsay, I appreciate it. Thank you everybody for attending. Today we're going to talk about the topic for pressure management. So I will get started right now. And as Lindsay said, if you can just save your questions till the end, we can address all your questions at that time. So first question is, why pressure management? Why is it important to have a pressure management program for your utility? So I just want to cover some of the most important aspects of why we want to be thinking about having a pressure management program. So fundamentally, it's to provide safe drinking water. Loss of pressure can allow intrusions and contaminants into your distribution system. Fluctuation in pressure can affect physical integrity of the pipes. That would be like pressure spikes can result in leaks, main breaks, and premature failures. And then also pressure management can save money for the utility by reducing energy costs, systems maintenance, leakage, customer complaints, and water quality problems. So those are all very fundamental reasons why it's really important that all utilities have a good and robust pressure management program in place. So today we're going to talk about 4 different case studies, and we're going to highlight the benefits, what was involved in the case study, the results of it. And I think that will give everybody a good idea of some of the value of having pressure management by seeing it as it's applied to some real life situations instead of some theory. So 4 different case studies we'll be talking about. First one is with Cucamonga Water District, and it's related around energy cost savings. The next one is South Feather Power and Water. That is focused on uncovering PRV balance issues. The next one is the Los Angeles Department of Water and Power. It's identifying the stuck valve at a pump station that we're creating many transients in their distribution system. And then finally, we'll talk about White House Utility District related to smoothing out pump turn on and turn off functions to reduce transients in the network. So 4 different types of case studies, but ultimately the benefits end up being very, very similar. So let's go into the first case study right now. It's with the Cucamonga Valley Water District. To give you a little bit of a background. So Cucamonga Water District is located in Southern California, provides water to around 200,000 customers. Energy cost is one of the largest expenditures of the district. So the district has created a primary initiative to reduce energy costs, and they want to do that by taking analytics and data and using real-time flow and pressure data for analyzing demand and supply. So understanding that background, the solution revolved around, first, we identified a test pressure zone and a PRV that feeds water to that zone. And then from there, Trimble installed its RU32 MA. It's a multi-channel remote monitoring unit connected to pressure sensors to monitor inlet pressure, that would be pressure coming into the PRV, outlet pressure, that would be pressure going out, flow going out, and then we also connected an insertion flow meter to monitor the flow. After everything was installed, we are going to use, or we use the software called Trimble Unity Remote Monitoring, which provided the visualization of the data and reporting that make decisions to reduce energy demand and consumption and still meet the customer demands. And then the final part of the solution is taking all the data that was gathered in Trimble Unity Remote Monitoring and integrated it into the SCADA system using APIs. So once we did that, the findings, as after reviewing of the pressure and flow data, it was really determined flow was being maintained at consistent gallons per minute, regardless of the demand. And the next slide will be a very good visualization of what we're talking about. Actually, before we get to that slide, wanted to talk a little bit about why energy cost is so important to just not only Cucamonga, but to all water utilities. And why now? Why do we want to be focused on it right now? So water and wastewater services commonly make up anywhere from 30 to 40% of total energy used in a municipality. So it's a large amount of energy that's being consumed by the water and wastewater service providers. And on top of that, the energy cost can be a large portion, up to 35% of the operational budget of any water or wastewater utility. So that's really second only to staffing or labor. So if you look at the pie chart that I have below, you'll see where that energy is being consumed. The vast majority of it, as you can see, 67%, the energy is being used to pump finished water. So it's a large amount of energy. It's a big expenditure to the utility. And utilities want to get a real good understanding of where they're spending their energy money. So by reducing that and still being able to meet the demands of their customers, they can save a great deal of money for the utility, and that affects the customer in terms of rates and being able to keep the cost of service down. So the energy is the largest single controllable cost at any water and wastewater utility. But you also have to note that energy costs have been going up very, very rapidly. And when most of these water and sewer facilities came online, energy costs were relatively low. And energy efficiency was not really a primary objective of the design process of the systems. But with a rising cost of energy, and now you have air quality issues associated with energy production, energy management has really risen to the very top of priorities in the water industry. So it's a huge expenditure, and also it now is really very important that all utilities get their arms around their energy consumption and their energy cost. So if you look at energy management as a whole, really what we're looking at is trying to reduce the operating cost, trying to shrink the environmental footprint, improve public acceptance, and improve level of service and water quality. So before we kind of get into some of the data, I wanted to kind of give everybody a real high level overview of energy pricing. Many of you that are online right now and listening to the webinar are obviously experts in water and wastewater operations, but a lot of you may not really have a full understanding of how energy costs are priced out and what they really mean. So let's talk about sort of the three different categories of energy pricing. One is consumption. That's probably the easiest one for everybody to understand. So it's measured in what are called kilowatt hours. So it measures the amount of energy used during any billing period. So as an example, if you use 10,000 kWh or kilowatt hours during a billing period, and your rate is 10 cents per kilowatt hour, your consumption charge is going to be 10,000 times 10 cents, which equals $1,000. Now that's a fairly constant number, but where it really gets complicated is when you start talking about demand. So there's a difference between consumption and demand. So what demand represents, it's the amount of power that has to be generated at any given time. So as demand increases, utilities, electric utilities, power utilities, oftentimes have to go out and find sources of other power that they can meet the demand at the given time. So what happens is they actually have to go out and buy power to meet these high demand periods. And so that gets very expensive. So what happens is that cost is passed on to the customer. So the speed at which you use electrical power is measured in what's called kW, or kilowatts. So the electric utility usually measures demand as an average of power that's drawn in any 15-minute period. So like, for example, very short burst of demand, for an example, when demand surges, when a motor goes on, it really won't have a great effect on the demand because it's averaged over a 15-minute period of time. But the longer periods of demand will have a huge impact. So for instance, if you leave a motor on all the time, and I used an example of like a kitchen exhaust fan, but a better way of thinking of it would be a pump motor. If it's turned on constantly and running constantly, it's going to have a significant impact on the demand. So along with that, not just demand, but there's another component which is called peak demand. So during peak demand periods, when energy is at its highest, as an example, 3 p.m. on a 100-degree day, that will be a peak demand period. Demand charges are even higher during that time. So in effect, if you take all these things into consideration, when someone or a utility gets their utility bill, they're going to have to pay consumption charges. They're going to also have to pay demand charges. And on top of that, if they're using a lot of demand charges during peak demand, they're going to be charged even higher for that. So oftentimes the demand and peak demand charges can be much, much higher than the consumption. So that's why it's really important for utilities to kind of understand all the components of energy pricing. So let's take a look at some of the data. So what you're looking at is the data that has been consumed by the pressure sensors and also a flow meter, all connected to a Trimble Telog device called an RU32MA. So it's bringing in 3 different points of data. So if you look at the chart, if you look at the red line, the red part of the graph, that is actually the input pressure reading. So that's the high pressure coming into the PRV that we're monitoring at this point. If you see the blue line, that's the flow. So you can see the flow rates are staying up in close to 100 gallons per minute, dropping a little bit, but kind of staying in that general range consistently throughout the day. Now, if you get up into right about here where it jumps up, you see that the pressure has dropped and the demand has gone up. So this is obviously during a high demand period for water. So the flow has gone up to meet that demand, but then it drops back down again. And then you'll see it again in another part of the day when the demand charges get, or when the demand period gets higher. Now, the green line represents the outlet pressure. So that's the low pressure reading that's coming out of the PRV after pressure has been reduced. So that's pretty consistent, probably in the high 40s. And you'll see that that is a fairly common thing that you will see. It's very consistent in going out into the network. So this is the data that was captured. This is sort of the baseline data. This was the data that the utility was looking for, which they didn't have visibility to before we installed the remote telemetry inside this PRV. So this was the baseline data that they got, and it gave them sort of a good screenshot of what was going on in terms of demand and supply. So after evaluating it, and you'll see this next chart that will tell the story. So it's quite a bit different than what the baseline is. So as you can see, again, kind of referring to the flow went up during high demand periods, which would be normal, but you can see where they made some really major adjustments. They dropped the flow down to 0, meaning they essentially had turned off the pumps because they were able to determine that they didn't need to be pumping water during this particular time. Then when the demands went up, pumps turned back on again, and the flow went up again to meet that demand. But again, it dropped down again to practically 0. For a long period of time. This is a 1-day period. So again, if I do a little bit of a comparison, if I go back to the original baseline data, you'll see that the pump is continually pumping water. You can tell by the flow. That flow is moving through the system consistently and all day long. So in effect, those pumps are working when they really don't have to be, based on the analytics that the utility did after they were able to analyze the data. So if you look at it, you'll see that the pump times were reduced significantly, which really reduced the energy consumption and reduced the demand charges and during major peak demand areas. It's a little bit hard to tell from this graph, but they also were able to reduce the pressure about 7 psi from the original baseline, which really helps in reducing mainline breaks and reduction of non-revenue water and liability claims too. So this is a very telling story right here. By being able to put this data to work, they were able to make some major adjustments to their pumps, to their pump run times, which ultimately are going to save a significant amount of energy costs for the utility. Now, this one utility has in the neighborhood of about 50 PRVs. So this was just done at one. This was done as really a proof of concept. So after they were able to determine the success of it and what they thought that the ROI, the return on investment, would be by saving energy costs, they decided that now they're in the process of rolling it out to all 52 of their PRVs. So as the data comes in, the consensus from the utility is that an ROI, the cost of the equipment versus what their energy savings will probably be somewhere in the neighborhood of 8 to 14 months for a return on an investment. So it's a very significant savings to the utility. And basically, this is really what we're talking about in terms of putting a pressure and flow management program in place and how it can benefit the utility. So, second case study. So this was with South Feather Water and Power District. And this is revolving around PRV management. So just a background, South Feather Water and Power is a water and service provider for several municipalities in the northeast section of California. It's a smaller district. The district network is made up of 12 pressure zones and about 20 PRV. When they started the program, they had no reliable method of monitoring pressure throughout their various pressure zones. So they really had no real-time visibility or operational awareness of any impact distribution on the distribution pipelines and other assets within their system. So the solution really, again, went through a validation phase. They installed just one hydrant pressure recorder, which is what we call our HPR 32IA, in one pressure zone that it was fed by 2 PRVs. And again, using Trimble Unity remote monitoring for the data review, reporting, and analytics. So the results by monitoring pressure coming off of those PRVs is that the first thing that they saw, that pressure in that zone was very, very unstable, with pressure changes of 40 PSI continuously throughout the entire period of time that pressure was being monitored. And there were also many major transients occurring during that time. So that led to an investigation by the utility from looking at the HPR data, pressure data, to do an investigation of the PRVs that were feeding that one particular pressure zone. And so what they were able to determine was that one of the PRVs was supplying 95% of the flow, while the other PRV was only supplying 5% of the flow load. So the PRVs were completely out of balance. They had no idea until they got this data from the pressure from the HPR. And so what the utility did was that they balanced out the 2 PRVs to supply equal amounts of flow. So you'll see it again in the chart that I'm going to show you in the next slide, but it eliminated all the transients that were occurring in the zone, and it reduced pressure on the pipe, which ultimately would increase the pipe life and reduce the risk of mainline breaks. And it also added life to the PRV valves. And again, the data and the picture will tell the story. So again, this is the baseline. This was the data that they picked up immediately after they installed the hydrant pressure recorder. It's pretty obvious by looking at the chart, as you can see how pressures were jumping all over the place, up and down continuously. If you look at these triangular boxes, rectangular boxes below, where it has S3 of them, that's an indication of water transients that are occurring. And the way we do the water transients is that we categorize them. We have 5 different categories. The 5 is the most severe, considered a critical transient. Then a 4, which is a severe transient. A 3 is what's considered a major transient. And then 2 is moderate, and then 1 would be a minor transient. So you can see all the instability of pressure in this zone. And this was happening because their PRVs were out of balance, but they had no indication that that was really happening. And it made them go back and take a look at their PRVs. So what was causing all these swings in pressure is because the one PRV was doing 95% of the flow load. It was continually turning on and off and on and off and on and off. So every time these valves were opening up and closing, it was creating this surge in pressure throughout the system. So if I go to the next slide, this is what the data looks like after they adjusted and balanced the PRVs. So you can see the huge difference. So they got rid of all the transients, and you can see now how stable the pressure is. Again, if I go to the first slide, this is the before or the baseline slide, showing all the swings in the pressure and the transients. And if I go to the slide after the PRVs were balanced, you can see the significant difference in how it leveled out the pressures. So that there was a significant benefit to the utility. So again, because of this, they are now going to be installing pressure monitoring and flow monitoring throughout all their PRVs in their system, so that they will have excellent visibility into what's going on. So the other thing to consider about monitoring a PRV is a lot of utilities do have SCADA systems, which does do a certain level of monitoring. But one of the blind spots of a SCADA system are at PRVs, because PRVs are generally located remotely and spread out through a network. It's really very, very cost prohibitive to put SCADA, meaning they would have to run power to every one of their PRVs to get any kind of visibility. So they really do a pretty good job. SCADA will do a pretty good job on, you know, vertical type of assets like a pump station, for example, but they really don't have a very cost-effective way of monitoring PRVs. Now, the Telog product is completely battery powered, and so we can kind of fill in the blind spots of where SCADA cannot provide that data. And PRVs are a significant, I mean, a very significant part of any utility, water utilities operation in terms of visibility and understanding if those PRVs are operating properly. And without that visibility, utilities then become very reactive. They almost have to wait for a major event to happen in a PRV, which could cause major events throughout the network. And then they have to react to it, which could create mainline breaks, major customer complaints, all sorts of things that will kind of create havoc within a utility. So monitoring PRVs are critical to any utility that has PRVs in their system. So let me keep on going. The next case studies is with the Los Angeles Department of Water and Power. So a bit of a background. LADWP, the acronym for Los Angeles Department of Water and Power, it is the largest water utility in the US. It's got over 7,000 miles of pipe. They have 120 different pressure zones, 420 PRVs. They have elevation ranges from 0 to 240 feet above sea level. Annually, they have around 1,700 mainline breaks a year, of course, resulting in millions of gallons of non-revenue water, and then, of course, millions of dollars in repair costs and insurance claims. So understanding what their problem was, LA has made a major initiative to create an entire pressure management system. They have a whole staff dedicated now to pressure management, to monitor and manage pressure throughout their entire system. So the ultimate goal is that they'll be installing over 1,200 hydrant pressure recorders, all capable of capturing transients with a sampling rate as high as 256 times per second, which is the highest in the industry. So the ultimate goal for them is to eliminate a high percentage of transients in their system and reduce the intensity of the transients, ultimately with the result of reducing the number of mainline breaks in their system. So just a quick understanding. So there's a lot of terminology, different types of terminology that are used for what's called a water transient. a better way, a descriptive way of identifying or describing a water transient would be a water hammer. So effectively, if you look at the picture on the left, try to imagine taking a hammer and with 100 pounds of pressure, smacking that pipe continuously. So ultimately, what's going to be the result of it? It's pretty obvious that over a period of time that you're going to see that pipe stressed to the point where it'll start creating leaks in it, underground leaks, which may not be able to be noticed. And then ultimately, you're going to get a mainline break. And if you look at the picture on the right, everybody has seen what a mainline break can look like. It can be catastrophic in for a number of different reasons. A lot of property damage can occur. A lot of liability issues that can happen. Disruption of service, stopping traffic for emergency repairs, health and safety to employees. So utilities at all costs are trying to reduce those mainline breaks. And one of the ways they can do it is try to understand water hammers or water transients that are occurring in their system. So I wanted to show you what a water transient looks like in high resolution. So if you look at the graph, this is data that is actually happening in almost megaseconds, right? So these are sample rates of 16 times per second. So it's happening so fast that a normal pressure recorder probably, in all likelihood, will never be able to pick up this water hammer because it's happening so quickly. So by being able to have the capacity to sample at a very high rate, our equipment can identify this water transient. So if you look at this one, if I look at what's going on, is that this is happening before the transient. So you can see the pressure is quite stable. And then here is the event itself. Pressure has dropped down to 100 PSI and then shot back up to well over 200 PSI. And then it continues through the remainder of that transient event. So again, if I go back to this picture, try to imagine taking a hammer with over 100 pounds of pressure and smacking that pipe, So the ultimate result eventually is going to be, it's going to break that pipe. So this is a high resolution view of what a water transient looks like at 100 PSI differential. And this was recorded at just 16 samples per second. Can be recorded at a much higher rate, but 16 samples per second was high enough to pick up this individual transient. So if I look at the baseline, you'll see that in this one particular location, and this is a very good view of measuring transients versus just being able to measure straight pressure. If I didn't have the capacity to capture a water transient, if I looked at this chart, to me, it would appear that the pressure is relatively stable. It's not moving around very much at all. But if I look down below where all the transients are occurring, you can see that there are many, many major transients that are occurring in here. So what LADWP did is after they looked at the data and were able to identify these transients, they traced it back to a pump station that, if you look at the map over here, that the location of the water hydrant recorder is right here, and relatively close by there's a pump station. So what they did is they went back to see what was going on at that pump station. And after doing a thorough inspection of the pump station, they discovered a malfunctioning valve. So they repaired the valve. And now, if you look at the data, you'll see that the pressure is stable. But if I go down to see where my transients are occurring, it's eliminated just about every one of those transients. And so that was their goal. They wanted to get rid of the transients. And they were able to identify, first of all, identify the type of transient that they were getting, how many they were getting, the intensity of they were getting at this location, and then be able to trace it back to a malfunctioning valve at a pump station. And so by repairing the valve, they were able to reduce the transients. So again, the benefits are reduction of the stress on the pipe, reduction of mainline pipe breaks, and of course they repaired the valve, which they didn't know was malfunctioning. And so again, it was adding life to the pump itself. So again, that's another good example of what pressure management can do. So the final case study is with White House Utility District, which is in the Tennessee area. So what this revolves around is, again, using an HPR somewhat similar to what happened in the city of Los Angeles, but a little bit different result. But again, by being able to get the data from the pressure recorder, they were able to make some adjustments in their system to reduce transients in the system itself. So everybody can see a picture of what the hydrant recorder looks like. It goes right onto the standard 2.5-inch thread on a fire hydrant. And this doesn't show the security cover, but typically you would see a security cover over the top of that hydrant that can be locked in place to, avoid any kind of theft or vandalism. But this is essentially what it looks like. It's a very simple installation, takes maybe 10 minutes at most to install one of these devices, and it's very mobile as well. It can be moved around very easily. So the first thing that White House did is they picked a variety of different locations for placement of their HPRs to track pressure and transients. So you can see the map and you see all the different blue dots. Those are where all the recorders were placed throughout their system. Then they focused on one particular pipeline that had a major history of major pipe line breaks over a period of time. So if you look at where the installation of the hydrant recorder, it's placed right here on the left, the far left. And then if you see the pipeline that is associated to this hydrant recorder, they identified 12. They had 12 major pipe bursts over a 1-year period of time. So they knew there was a lot of things going on that were stressing that pipeline. And they wanted to focus on what was going on. Why were they getting so many pipe bursts in this one particular pipeline? So they associated it to the pump station that was pumping the water through this particular pipe area. The Slater Creek water pump station, it's got 450 horsepower pumps with frequent on and off cycles, so discharging pressure influences. So you have the three components. You have the hydrant recorder, you have the pipeline that has had a history of major pipe bursts throughout a year, and then they focused on that particular pump station that was feeding the water to this particular pipeline in this area. So again, you look at the data, And a little bit like the data that we were seeing in Los Angeles, the data looks relatively smooth until you started to pick up the transients. So there really wasn't much drop in pressure until you could pick up the transients. So the thing that was really interesting, what Whitehouse did, if you look at the chart, a little hard to see, but you can see the icon where this was a transient event. They overlaid the pump run times and cycles, on and off cycles, and identified them and correlated them to when the transient was occurring. So if you see right here where the arrow is pointing, there's a transient at the pump off event. So the pump turned off, boom, there's a transient right here. If I go to the next one, again, you can see the rectangular, which is the identification of the transient. Again, the transient took place at the pump off event, just like the first one. Same thing is repeated right here. And again, the same one is repeated to the far right. So there's definitely an association of the pump turning off and a transient occurring through the system. So if I go to the next slide, this gives the higher resolution of that transient. So if I look at the blue, if I see the blue box right here, the yellow box will show the 1 second interval, which is really kind of a normal sampling rate for pressure. It looks relatively simple, but when it went into the impulse or transient mode, it revealed that there was a PSI differential of 80 PSI pressure swing that wasn't visible in the normal sampling rate and the 1 second interval. So you can see the blue lines as the transient occurring. So again, you can see this transient. This is happening in milliseconds, right? Well under a second. So it goes down to 139, it jumps up to 216, and then it's bouncing around. So again, going back to that picture of the water of the hammer hitting that pipe, that's what is really occurring. So this movement that's happening so fast and so intense is like taking a hammer and smacking a pipe with over 80 pounds of pressure on it. And everybody knows if you continue to do that, what the end result is going to be on that pipe. So what did they do? After they were able to find this data, they put a plan in place. So they went to the pump itself. They adjusted the pump control valve for closing and opening to slow it down, to slow the valve movement and hopefully settle the transients. And then they went back and they monitored the pressure after they made the adjustments in the valve to see what kind of impact it had on the transients. So everybody can see that this is the valve here. They made the adjustment in the valve and how it was opening and closing. They slowed it down so it wouldn't create, the theory was if they can slow it down and smooth it out, that it would eliminate or reduce the transients that were occurring. So the control valve was adjusted to pumps 1 and 2 to slow the opening and closing speed down. So if you see now, what took place is that the pressures had smoothed out considerably. They were still getting some transients, but many less and much less severe. So it's something that they're still investigating. But again, if you look at the benefits of pressure management, of having the data available to you and being able to take actionable, do actionable things that will combat and deal with some of the events that are happening, is that it has significant impact and benefits to your utility. So just as a review, we'll go over the immediate benefits of having a pressure management program in place. So again, immediately it can lower the average pressure zone, the average pressure zone, can reduce leaks and distribution input, can reduce energy, CO2, and chemical cost, makes water efficiency saving results from reduction in demand. So the long-term benefits are lower burst frequency and system protection, reduction in repairs and maintenance, reduction in insurance claims and liability, reduction in pressure complaints, interruption to supply improvements, increased security of the supply, and it can also defer capital costs for network assets. So these are just some of the overviews of what some of the benefits of having a pressure management system in place. So a lot of utilities, just to briefly summarize, a lot of utilities do some form of pressure monitoring. But if you really look at it in sort of a global view, a holistic view, that you can actually get a lot more benefit by putting a comprehensive pressure management program in place, as opposed to just doing periodic measurements for pressure. A lot of utilities will do it to help calibrate their hydraulic models. They'll use these pressure recorders to go out and deal with customer complaints. But it really isn't you're not really getting the full value of having an ongoing pressure management system in place where it's giving you real-time visibility into exactly what's going on in your utility and then giving you the information that you need to go out and make the adjustments that are required. So basically that includes my portion of it. Lindsay, I think we've got about 10 or 12 minutes left. So if there are any questions, I guess this would be the time to take them right now.
Yep. If anybody has questions, go ahead and type them in the question box and we'll read them off and Dave can answer them. As of right now, we don't have any questions. Just as a reminder, this webinar was recorded and will be sent out to everybody tomorrow. Let's give it another minute, see if any questions come through.
Okay.
And if questions come up after the webinar, feel free to reach out to myself or to Dave, and we can get those questions answered for you. Okay, well, I don't see any questions coming through, Dave, so thank you very much for today's presentation. I hope everybody enjoyed it, and if there's anything you need, please feel free to reach out to myself or Dave.
Okay, thank you, everybody. Much appreciated.
Thank you.
Bye-bye.